Okay, thank you very much, Roland. I hope everybody can hear me, and hello from my side. My name is Christian, and I'll give you some ideas and want to tell you about some topics in the direction of radar data assimilation we do at the German Meteorological Service. And as Roland already said, it's not only direct data assimilation of radar data, but also derived objects. And before I want to get into the details, I want to follow the golden rule of look at your data, and in this case, look at your observations. So this is the radar network of the German Meteorological Service. I don't want to give you all the details, but just tell you that we have like 17 radar stations covering all German terrain, and all of them perform a synchronous scan strategy. We have 2 scan strategies. They are also synchronized, one volume scan where you sample the volume and one terrain following precipitation scan. Next, I want to talk about my outline here. So in the left corner, there's the data I just mentioned. And then one topic I'll talk about is the direct assimilation of this data. And in this case, if I say 3D radar data, I not only talk about reflectivity, but also about radial wind. And then there are many more boxes and circles, which I'll also talk about. First of all, I want to mention that I'm part of a project called SINFONY. And in this project, we want to bring Nowcasting and NWP together. And we want to bring that together in terms of precipitation fields, but also in terms of reflectivity objects you might see in Nowcasting techniques. So objects, in this case, let's start up here. Where I say object generation via Nowcasting object ID is something you could imagine as convective cells, for example, you try to detect in your radar sweeps. And you could go ahead and try to assimilate those guys directly, which is a tough kind of work because you have to do some matching, which I might come back to later. But you could also assimilate those things indirectly as what I call feature assimilation. And the idea behind that is inspired by the fraction skill score. Additionally, as a pre-step and some additional tests, we also look into the object generation in the way of thresholding composites. So we look at our reflectivities and threshold them at some reflectivity scale, and then also look at them in the idea of the fraction skill score and assimilate these things. And later on, I'll show you some results for first experiments we've performed for that. So talking about data assimilation also means talking about your system. My system is the KENDA system, so I work on regional NWP. KENDA consists of the 4D LATKF following Hunt et al., and I assimilate conventional data, including the mode S data, and if I mention it, 3D radar data or some of these derived objects. Usually, KENDA runs currently in the operational mode with latent heat nudging, which I don't use in the experiments I show you. So coming to KENDA briefly, KENDA consists of an ensemble of forecasts or ensemble of model runs where we use the Cosmo model. And since I took the picture from the paper, they're still saying with latent heat nudging, but forget about that for the moment. So during the model runtimes in this ensemble, I get ops minus first guess written by the model at observation time. And these guys then serve as input into the LATKF to compute my analysis ensemble. Additionally, I have an independent deterministic control run, which gets information about how the ensemble changes via the Kalman gain. So in some sense, you assume that your deterministic control run behaves like the mean of the ensemble. For all that, I also need a forward operator, of course. I use the efficient modular volume scanning radar operator in this case. You can read about that in Zeng et al. Okay, let's start with the direct assimilation. For now, I first give you some details about the techniques I do, and then I come to the results. For the radar data assimilation, I use a similar setup as Big et al. 2016, but additionally with radial winds. The difference is that I looked also into the de Rosier statistics for the radar data assimilation and the radar data itself. For the reflectivities, for the radial winds, Elisabeth Bauern-Schubert did that. And I used this height and elevation dependent observation errors in my experiments. And additionally, which is in some sense similar to the things we talked about this morning, is that I say we need a trigger for missing convection. This is a little bit of a different perspective, and we'll see in a minute what I mean with warm bubbles, which is another technique than latent heat nudging, which is something helping you if you have no spread in your ensemble, if you miss convection or precipitation, helping you to gain this spread according to the observations. Some more details. The observables I use are reflectivity and radial wind, only of the volume scan. And for the reflectivity, I use all 10 elevations. For the radial winds, only 3, which seem to be preferable for in terms of the scores. In a temporal resolution, it's the same. I could have every 5 minutes radar data, but I only use the radar data at analysis time, so every 60 minutes. With a spatial resolution of 10 kilometers, I use a kind of super obbing. I don't want to go into much detail about the super obbing. I guess it's known to most of the people. Just so far, I use a Cartesian grid with the grid spacing of 10 kilometers to find super observations. So I average observations in, for example, this red box, and put this observation in terms of radar observations back to my radar grid, which I later assimilate. Okay. So, as I said, we need a trigger for convection. Otherwise, if we have no spread in the ensemble, we cannot do anything. Oh, as we learned, we can do something. And I used the warm bubbles instead of the latent heat nudging. I think last year, Alberto de Loza in Munich already talked a little bit about that. Just to remind you a little bit, what I do is I look in my observations in the radar composite and check if there is, in my model, something missing. And if there's something missing, I say, okay, I try to see if only a trigger was missing or if the model doesn't see possible convection at all at this point. So I look for cells, and then I start heating up the model at this point, keeping the relative humidity constant, and a warm bubble could evolve. The positive thing about this is the model does the dynamics for you. You just give the trigger, and it starts doing it if it wants so. It's different from latent heat nudging. Latent heat nudging would adjust the model at every time step of the model. Okay, now coming to what I call texture assimilation. That's the first kind of object assimilation, where I look at radar composites and threshold them. So I get afterwards a binary field saying, yes, this pixel is above the threshold or below the threshold. This is one kind of indirect assimilation. As I already mentioned, it's in the spirit of the fraction skill score. And we've seen yesterday a poster by Shigenori Otsuka, who also presented some results in the speedy LATKF setup, where he looked at precipitation in a climate mode. And this seemed very promising, and he's seen also positive results in that. Okay, what's the idea behind it? As I said, I threshold my reflectivities. I get a binary field, and just for illustration, I say pixels which are higher than the threshold are in black, and I create some sort of pseudo-observation. This is the red box in the middle, and I take an area around this pixel and count the pixels or the model grid points which succeed the threshold. So in some sense, I blur out my information, or I average it again in the box to, in some sense, this is inspired by the idea that we don't expect to resolve the model to resolve precipitation directly at the same point as in the observation, but we give it some possibility to be at least close by. And I not only do that for one pseudo-observation, but for many. And in this sense, I scan this binary field of information from my model and my observations, and I get numbers for the LATKF, so ops minus first guess, to compare to each other. And we'll see later that this is already a very powerful tool to assimilate radar data. Okay, the next thing I want to introduce you to are the features. This is inspired by the Nowcasting object identification. Very briefly, I cannot explain the whole algorithm. They have an adaptive thresholding at the radar reflectivity pictures and create 3D cells out of that. So I really get 3D convective cells, or something we think of as convective cells. And also we have tracks and forecasts available from these guys. And in the same spirit as before, we can assimilate those by looking in these boxes and, for example, look at the spatial distributions of features or these objects and a number of features in the area, or, for example, quantities like the mean distance of features in each box. Or you could also think of the vertical integrated liquid or lightning activity. And just to illustrate that again, I have the same picture as before. And the difference now is that all these black pixels know they belong to one entity. So they can have collective attributes. This is the real difference between these objects, in the sense that I have found some by an identification algorithm, and single pixels. So suddenly I have the possibility to say, well, there is a convective cell, and I also expect something like a cold pool or lightning to happen. And if there's lightning, I can also say, well, if there's a lightning jump, I can assume hail to happen or something like that. And again, I can look at my pseudo-observation, and for example, here I could count the objects which touch this box or are inside the box for the observations and also for the model. And then I can compare these numbers and judge how good this ensemble member, for example, would be in terms of objects. Okay, and I can also create more pseudo-observations for that. For now, I also only show you results comparing the direct assimilation versus the texture assimilation. For the objects, for the nowcasting objects, I'm still doing the work in the background, so read in and stuff like that. So here I show the results for the data assimilation cycle, first guess and analysis, RMSE. And I compare in green the full 3D radar data assimilation, including radial winds, using also bubbles. In blue, the warm bubbles. In blue, the texture assimilation. And in red, as a reference, no radar data assimilation. And I didn't forget the warm bubbles here. I didn't use them here. OK, and for the relative humidity, we don't see so much impact, a little bit on the positive side for the full 3D radar data assimilation. The temperature throughout the whole atmospheric column seems not to be very dependent on what I do. So nothing harms it, but nothing improves it so much. But for the wind, which is the horizontal wind, we see a big impact of the 3D radar data assimilation, which of course makes sense because since we assimilate radial wind velocity, which of course helps that. But especially for the texture, we see that it's also improving against no radar data, which came somehow as a surprise to me. So we're doing also something right here. The statistics I took is about 14 days with an hourly cycle and 40-member ensemble, but we only look at the deterministic evaluation here. And the verified observations for this statistics here are all the same in the experiments. Next, I want to take you to the forecast verification of the reflectivity for 6 hours. Again, in green, full 3D radar data assimilation, in blue, texture. In red, no radar data. This is the same period, 14 days. And now we look at 6-hour forecasts issued hourly between 10 and 18 UTC. This is basically the very active time for Germany. And again, at the deterministic run. And this time, I also evaluate or verify these reflectivities by using the fraction skill score. And let's first look at the bottom box here. This is for the fraction skill score. You also need a threshold, which you evaluate for. I took 30 dBc, and you see for the texture, I also took 30 dBc. And it's very impressive that the fraction skill score at this point is basically the same for the full 3D radar data assimilation and the texture assimilation. This is quite stunning, I find. However, for the 20 dBc, which you can view as I didn't really assimilate so much data at this point, there's the 3D radar data much better than the texture, and of course also the 30 dBc count in here as well. Just for the end here, I compare the 3D radar data against no radar data, so no texture at all. One of my colleagues said if you would have been 10 years earlier, we would have introduced the 3D radar data assimilation instead of the latent heat nudging. We see that we do a lot of good things with the 3D radar data assimilation, a lot of green. It improves many things, wind direction, wind speed, relative humidity, and temperature in a 24-hour time scale. in the column and at the surface, which I find quite impressive, and we're going down the right way here. For the conclusions, it's basically all I said for now. We see a big positive impact of the 3D radar data assimilation compared to no radar data assimilation. And I didn't show, but it's the same in the precipitation verification in this case. And if I compare against the operational system, the results are, of course, not so good because we assimilate via the latent heat nudging reflectivity, or at least radar data in this sense. It's comparable, but not as good. I still have to work a little bit to beat the operational system. For the texture, we see positive impact, but there are open points which I have to investigate, and also some negative points we have to think of if that's really what we want to do. And for the features, I hope I can show you next year in the US what we are going to do there, or what results we found. And with that, I thank you for your attention, and I'm happy to answer your questions. Yeah.